Hello, good evening. I'm going to try and help you to get to grips with thermal mass and how thermal mass in buildings, principally masonry, concrete and other such weighty materials, can make a fundamental difference to the way that a building services engineer would go about then designing the mechanical and electrical installations, and how the overall system of a building comprising thermal mass, people and mechanical electrical installations can therefore operate very much more efficiently than if those systems were designed as individual separate items. And in order to illustrate that, I'm going to show you the Innovate Green Office, which is sitting on a developer park just on the eastern outskirts of Leeds, not very far from here, possibly worth going and having a visit if you've got a few hours to spare. Briefly, I'll introduce Innovate. Trust me, the design team did not choose the name of this building. We were landed with a developer that had already chosen to call themselves Innovate, and they wanted us to do something novel. So unfortunately it got branded as the Innovate building, which makes it quite difficult for all of us, but we have to live with it. This was Innovate's first building. It was a standard air-conditioned with VRF split units, if that means anything to some of you in the room. Standard office on a developer park at Sherwood Park, just outside Nottingham. Completed in 2002, lowest common denominator of commercial building that you find anywhere in the UK. BREEAM didn't get anything. In fact, they didn't even apply for it. And it cost the princely sum of about £64 a square foot to build and fit out to Category A. A very, very cheap building indeed, and absolutely bog standard in terms of its carbon footprint, efficiency and all that. An absolute bog, to be honest. The same developer and the same architects went on to produce 2 or 3 other buildings in the period in which we were consulting on and designing the Green Office in Leeds. The reason why the Green Office in Leeds took so long was because it was a very unusual and a very challenging building for the commercial market, for the speculative market, and it took quite a long time to come up with an appropriate package to put the funding together for that building. So in the meantime, the next office was Site 19 at Sherwood Park, just round the corner from their first office, completed in 2004, spent a little bit more money on it, you know, sort of slightly flashier cladding and some curvy, some peculiar angles and things like that. And with a bit of shoehorning, managed to get a BREEAM very good. The final office at Sherwood Park, known as Core 27, I have no idea why, spent a little bit more money on it again, not very much, completed another year after that, and with some real pulling and twisting and tweaking, managed to get up to excellent for BREEAM. Now, I don't know how familiar you guys are all with BREEAM, but it's been recognised that although BREEAM was the absolute pioneer in terms of environmental assessments, that it had fallen out of date over the last few years, and it was becoming increasingly straightforward to achieve a BREEAM excellent, especially when people were already complying with the new Part L 2006 building regulations. So actually BREEAM was completely revamped and a new BREEAM scheme was launched last Tuesday. So if anybody's interested in BREEAM, go and look that up on their website. But with a lot of manipulation, this scheme managed to achieve a BREEAM excellent, even though it was still based on the same fundamental design characteristics as the first building. It's still a fairly poorly designed and fairly poorly detailed. I don't mean that in the rude sense. You know, these are good guys, these architects, and they work very hard. But in terms of the bigger scale strategic thinking, it's still a standard developer office rather than a holistic building construction. And then, of course, the Innovate Green Office at Thorpe Park, which was completed beginning of last year, fully fitted out by last summer, and is gradually becoming occupied. It's currently about 40% occupancy. Considerably more cost involved in this building because it's an absolute prototype building. It's the first of kind, and there are a number of aspects to this building that would not be repeatable costs in a rollout version, pushing the cost up to about £135 a square foot. Interestingly, although that's a significant budget over and above the developer's previous cost models. We've just been talking about a job today in the centre of Wakefield where the build budget for that one for a commercial office building, headquarters building, is actually £135 a square foot. So this is not, in real terms, an expensive building. It is a speculative office building. Innovate are a developer and they develop and sell on buildings. But they also have a strand to their business where they operate serviced offices out of some of their premises. So they build, sell to themselves and operate. And they provide working space for small businesses, startups, technology businesses, people who are looking for office space, a receptionist, meeting rooms, telephone lines, that sort of thing. We all know the stuff, you know, the standard Regis model. But these guys are looking for a unique selling point, and the unique selling point in the case of this building was its environmental credential. So it's genuinely a speculative office because there are no tenants at the time the building is built, there are no tenants at the time the building is sold from the development arm to the operation arm, and it relies entirely on the marketability of the building to bring in tenants and generate the revenue. So in that sense, it carries all of the risk of any other speculative commercial development. And that's what makes this an interesting construction, because by manipulating the building design and using materials and systems in a novel way, we're able to create a building which is of the kind of standard of environmental efficiency that you would normally only see in blue chip headquarters type buildings delivered into the speculative market. Right back at the beginning, the ambition for the building was set out to create a step change in commercial speculative design, to prototype a new kind of building, to make sure that it provides a very pleasant and atmospheric working environment in order to encourage the punters to come in and pay up their cash in terms of rental space. It clearly had to meet institutional investment criteria as a speculatively funded building, and that put some fairly severe constraints on the design team to reduce the life cycle and the operating costs for the building, and to demonstrate the reduction of those operating costs so that next time a building like this is produced, the developer has the leverage of demonstrable running cost savings in order to generate additional capital budget to fund what on this building would be extra overcosts, but on the next building just becomes part of the standard building model. To manage and reduce waste during construction, and to maximise the use of recycled and recyclable materials. Excuse me. The commercial funding criteria were the biggest constraints on the construction of this building and on the design of this building. If we look back at the examples that Stephen was showing you of concrete buildings for blue chip clients, for single purchasers, they can play with ideas like completely naturally ventilated, completely passively conditioned buildings, because they are their own occupier and they will tolerate out of condition temperatures, out of condition circumstances in the summer months particularly, whereas somebody who's got a choice of 3 or 4 serviced offices in the same location, if it gets too hot and too sweaty in their office during the summer and they're on a month's contract and they can cancel and walk out at any time, we don't have the option to be quite as free with design parameters for the temperature and for the internal environment conditions that we would be with an owner-occupier or a similar sort of institution. And in order to maximise the rental return on a specky office building, they needed to cram as many people in potentially as possible. And the combination of an occupancy density of 6.5 square metres per person and a limitation on the peak summertime temperatures to an absolute maximum of 26 degrees means that there was only one solution for this building, and it had to be mechanically cooled. It is not possible to achieve those environmental design criteria with a naturally ventilated building. The occupation is too dense, there's too much heat gain, and you can't discharge that level of heat gain in the summertime in order to limit the peak temperatures. So that immediately starts ruling out certain aspects of what would otherwise be design freedom. The fresh air supply of 15 litres per second is a requirement laid down, encapsulated now in the BCO specification. But interestingly, we actually preempted the latest edition of the BCO specification in that we selected temperatures not exceeding 26 degrees for the design criteria back in 2002, and it was in 2003 or 2004 that the latest BCO guide relaxed its specification for summertime temperatures from 22 degrees to 26 degrees, allowing designers much more freedom for environmental design. And obviously, in order to convince everybody that this was a commercially fundable building, we have to comply with all of these, and office lighting levels typically to 400 lux as well. So the solutions included a whole host of passive design solutions, including super insulation, the thermal mass, which we're going to talk about, design for daylighting, using the building structure as thermodeck in order to boost the thermal mass of the building, coupling all of that with heat recovery to minimize the energy spend into the building, using night cooling and mixed mode ventilation for passive summertime cooling, coupling it up with a trigeneration system, so for combined heating, power and cooling system. Using rainwater for toilet flushing, which is not new, but coupling that with a vacuum drainage system, which reduces the volume of water required for toilet flushing very dramatically, and putting in the usual systems, things such as high efficiency light fittings, lighting control systems. Through the work that Rio, the architects, had done previously with Innovate, they had developed an optimal floor plan for this business model, based on somebody being able to rent anything down to an 18 square metre office up to an entire floor plate. So this diagram just shows you the maximum possible population of 18 square metre office, 3 people in each of those offices, a central circulation corridor, fully cellularised, and a very, very high efficiency. This building actually achieves an 86% gross to net. Now, the guidance for architects is that best practice for gross to net on commercial buildings is something above 80, 85. So this is a pretty good and efficient office in terms of the rental return from the net lettable area to the gross area of the building. For an environmental designer, it represents an absolute nightmare. The degree of cellularization that's potential in this building completely obviates any potential for natural ventilation, because there are simply no connected ventilation routes through the building. Everything is hived off. As I said, 6.5 square metres per person approximately. Typically a passively designed low energy building would be designed for an occupation density of 10 or even 12 square metres per person in order to give the building volume sufficient to absorb the energy that's being introduced from people and from computers and from work processes. But this plan, as I say, it works extremely well for a serviced office developer. So this is the plan form that was adopted really as a result of that empirical work that had been done on previous Innovate projects. And by the time we came up with the number of car parking spaces that were demanded by Leeds city planners, the site ratio meant that we had to develop the block building into 2 blocks of multiple stories. And in order to keep down the surface area that was available to lose heat through, I haven't got the next slide yet, I'll come to that in a minute, developed it as 2 linear blocks of accommodation separated by a glazed atrium street. The glazed atrium street shelters the facades of what would otherwise be independent blocks of accommodation, and it reduces the heat loss from those facades because the atrium is in its own right a semi-heated space. So it's a hybrid of a linear block developed in response to the planning requirements for the occupation, and in response to getting sufficient daylight to each of those cellular offices, and then it's arranged with this atrium in order to get as close to a cube construction as possible in order to minimise the surface area that's available to lose heat for the internal volume that's enclosed. The reason why we started off by looking at the heat loss issues was because if we look at the broad spectrum of buildings in the UK, heat loss, or the heating requirement for buildings, is by far the biggest contributor to the carbon footprint. In fact, 44% typically of all the carbon emissions from buildings in the UK is associated with keeping them warm and comfortable in the winter. Heating, fortunately, is very easy to deal with. You just build your buildings right, you insulate them properly, and you make sure that the air doesn't leak in through gaps in the construction detailing, and you can very significantly impact on that space heating requirement. And that's what we did with Innovate. The Innovate building is designed like a storage heater. I don't know if any of you still live in houses or flats which have got electric storage heaters, and if you do, whether anybody's taken one apart to see what it looks like inside. But an electric storage heater is basically a big box full of bricks with a heating element and wrapped in insulation. And you turn on the heating element at night when electricity is cheap, you heat up the bricks. In the daytime when the electricity is expensive, you turn off the heating element and you open a flap damper on top to let the heat out that's been stored in the bricks. Exactly the same as if you went camping as a kid and you built a campfire and put a load of rocks around the campfire and then took a couple of the rocks into your sleeping bag to try and keep warm at night. Yeah? Masonry materials, heavyweight materials, have this property of storing heat and retaining it. And so this building is designed as a big, big storage heater. It's concrete construction, concrete framed, and it's wrapped in a very, very high level of insulation in order to trap any heat inside the mass of the concrete and not to let it out again. So the U values of this building typically exceed the 2006 Part L requirements by 50%, even though it was designed and assessed under the 2002 regulations. So, thermal mass. I've started to talk about thermal mass with my rock in the sleeping bag analogy. Thermal mass is nothing new. Clearly, you know, campfires, people have been building campfires and lining them with rocks for millennia. The Romans were a pretty intelligent lot. They didn't just invent concrete, they invented the use of thermal mass in buildings, as we understand it. The image on the left there is a hypercaust from underneath the bathhouse at Chedworth Roman Villa in the Cotswolds. And the way they kept their bathhouses warm, and this is about having even distributed heat over a large space, was the way they kept them warm was to build these labyrinths of channels in the ground underneath their fine mosaic floors, with a chimney at one end and a socking grate fireplace at the other end. And they'd stuff as much wood and combustible material into the fireplace as they could, light it, and the draft that's induced by the chimney at the far end of the floor void would draw the flames through the floor void. And obviously, if there wasn't anything in there to moderate that, some bits of the floor would become dangerously or uncomfortably hot, and other bits of the floor would still be pretty cold. But they got the idea fairly early on in civilization terms that lining those labyrinths with a thermally massive material, stone, meant that a lot of the heat energy was not transmitted directly into the space, but went to heating up the thermal mass of the labyrinth, which then stayed warm for hours. So you could build this socking grate fire, big furnace in one end of the hypercaust, burn it for a couple of hours and keep the bathhouse warm all day. Okay, and that's the effect of thermal mass. Our Mediterranean cousins know all about thermal mass. It's where they keep their most precious possessions. The thermal mass of caves we're all completely familiar with. Anybody who's ever been into a show cave knows that it doesn't matter whether you visit it in the middle of the winter or the middle of the summer, it's still pretty much the same temperature underground. Now that's a result of the thermal mass of all the rock and the earth around the cave absorbing any changes in temperature from air that's drifted into the cave from outside. So warm air drifting into the cave during the summer, all the heat is sucked out and absorbed by the thermal mass of the surrounding ground. And in the winter, cold air which drifts into the cave, is heated up by the energy that's been stored in the thermal mass of the ground. In fact, if we go more than a couple of meters below the ground surface, we get to this constant temperature. And if you measure the temperature in the ground beneath our feet, it actually turns out to be the average summer-winter air temperature across the planet. The planet itself acts as a big thermal mass store, and it averages out the summer sunshine and the winter frosts and stores all that energy below our feet. And that's what the winemakers use in order to control the climate in their caves. I'll use another example. This is a building without insulation or thermal mass. A couple of happy chappies that I once took on a D.V. expedition, I think. You know what happens, don't you? As the temperature goes up and down, day or night, outside the tent, the temperature inside the tent does exactly the same thing. There's no insulation. Insulation just slows down heat flow, but there's no thermal mass. There's nothing to hold the heat inside this structure and keep it up to a comfortable temperature when the temperature drops at night. Conversely, we're all familiar with churches, cathedrals. Yeah? Another example of a highly thermally massive structure, but still no insulation. Okay? The Gothic revivalists did not build cathedrals and then plaster insulation all over the outside. These are solid stone and solid masonry constructions, no insulation. But yet we know, don't we, that the effect of the thermal mass in these buildings moderates the temperature inside compared to the swing in temperature that occurs outside. I've got another example. Getting bored yet? Has anybody got any questions about thermal mass? If we look at a typical load profile in an office building over the course of an occupied day, we see fairly distinct typical characteristics. Right at the beginning of operation, prior to normal office hours, the building opens up, the lights are switched on, the cleaners turn up, you know, the hot water cylinder starts heating up, all those kind of preparatory things that happen in order to get our buildings ready for us. Start of occupancy, everybody arrives, every human being brings with them 100 watts of heat gain, and then they turn their computers on, and they turn their fax machines on, they turn their printers on, and they add typically another 150 to 200 watts per person of gains from office equipment. And the loads in the building shoot up. And then they stabilise because everybody's in, everybody's working, everybody's beavering away, until the sun swings around and the sun shines through the windows, and suddenly the load goes up again with the sunshine coming through the windows. And then as the sun moves on, the loads drop back down to that kind of steady base load of occupancy. The loads drop off at the end of the day, and you've got a little bit more cleaning, bit of security, maintenance, what have you going on, and then everything shuts down. At night, once the building is empty, the air temperature outside drops relative to the air temperature inside the building. And you get heat flow out of the building through the windows, through the insulated walls and the roof, and through any air leakage. So you see a negative heat gain overnight when the building just cools down and relaxes naturally. You can draw lines on that which indicate the two peaks and the median point. And what the thermal mass of a building does is help us to manipulate these profiles. In an ordinary lightweight construction, a bit like the construction we're surrounded by here, you know, plasterboard, timber, a little bit of cladding, possibly some exposed masonry here and there, but not a terribly heavyweight building. The temperature swings in the building, the temperature swings up and down above our desired control point, mimics the load that you put into the building quite closely. There may be a delay of an hour or so as the small amount of thermal mass in the building absorbs energy and gives it up again. But really the building is in a fast response cycle. And what this means is that all the energy that's coming into the building during the day is lost again at night and is of no benefit to us. And in the morning, we've got to build up that energy again. At the start of occupancy, we've got to start building up the energy in order to get the temperature up to a comfortable level before the start of occupancy. This typically means that even though during the day there's more than enough heat being generated in the building to keep it up to temperature, in order to get it comfortable for people to arrive, you've got to have a second-grade boiler plant in the basement in order to get the building started. Introduce thermal mass, and the storage capacity of that thermal mass starts to create a time lag. As energy is introduced into the building responds more slowly because energy is being absorbed into the fabric of the building, not just into the air contained within the building. And the combination of building fabric and air has much more thermal capacity than just the air on its own. So as we start to increase the thermal mass in the building, we create this lag which pushes the response of the building back in time relative to the heat gains. And you get to a point with a little bit of thermal mass in buildings, not a significant amount, but a little bit of thermal mass in buildings, where at the end of the daily occupancy, you're actually reducing the temperature that's been experienced below the peak. Your peak temperature is starting to occur in the evening after everybody's gone home, which is great because it means we don't have to deal with it. The building's empty. There's nobody to complain about overheating. So pushing that temperature peak back into the evening period is a tremendous benefit as far as a building services engineer is concerned, because they don't have to deal with it in terms of big plant, big chillers and things like that. And this is the sort of thing that building services engineers should be doing every day, and this is the sort of thing that you can be doing in every building you deal with if you think a little bit about how you can connect the internal environment, the air volume inside the building, with thermal mass, either in the ceilings or in the tops of walls, possibly even in the floor. And it doesn't take very much to do this kind of manipulation of the daily peak. However, if we get enough thermal mass altogether in the building, we can push that delayed peak right out into the nighttime, and we can bring forwards the reverse response to the nighttime cooling into the occupied day period. Okay, I'll come back to the heating issue in a minute. Push this peak right out into the nighttime period, then the peaks that are occurring during the occupied day are very much less. And this is what we tried to do with the Innovate building, was to produce enough thermal mass within that building that we took the unequal heat gains from the day with the heat losses from the night and averaged it all out to produce a nice smooth sine wave response in the building, and then manipulated that sine wave using heating or cooling mechanically as required. I'm going to put it in a slightly different way. Excuse me. Because this is how a plant engineer looks at the building response. Okay? We have to design, as a plant engineer, you have to design a chiller, a piece of machinery that will discharge all of the heat gain that's occurring at this peak during the day in a slow response building. Most of the time, though, the chiller operates at a much reduced level, and it only peaks on those coincident summer days where you've got the hottest outside air temperatures and you've got the sun shining in through the windows and a host of other coincidental peaks. So in terms of plant operation, it's quite inefficient most of the year because you've got a socking great piece of plant which is working at much less than its rated capacity. And any piece of equipment that works at less than its rated capacity works at significantly reduced efficiencies. So a chiller working down here relative to its peak capacity is not just working at a third or two-thirds reduced output. Its efficiency at that output may be only 30 or 40% of the efficiency that it would be achieving at a peak output. So it has a really severe impact on the design of plant and systems, and mechanical electrical engineers have all sorts of strategies to overcome that, such as putting in multiple chillers, multiple boilers, firing them all in sequence and things like that. But you're still only operating this chiller during the hours of occupancy. At this stage, you're not making any use of the thermal mass at all. Now, imagine what I said earlier about using the thermal mass storage to push out the impact of those loads into the nighttime. And it's a bit, I don't know, but it's a bit conceptual, but this is effectively what we're doing. We can chop the top off the daytime peak loads and drop it into the nighttime cooling well and average out those loads over 24 hours by using the thermal storage capacity of the building, and in doing so reduce not only the installed chiller capacity, but create conditions where you've got potentially fairly similar chillers, one of which may be called on to run 24, and you're using a second chiller for an extended period at peak efficiency, and using the thermal mass of the building to store the difference between the chiller output and the actual demand hour by hour. I'm going to pause at that point because I know questions are going to come later, but if anybody still doesn't understand thermal mass, please put your hand up now. No, we're getting there. Great. Myths about thermal mass. And this is my plug for our hosts, the Concrete Centre, and woe to the Steel Construction Institute. Thermal mass is very, very difficult to define. It's almost impossible to come up with a particular formula, set of characteristics that says, you know, something's going to be thermally massive and it isn't. It's about a whole host of things. The most important things that we consider are the thermal properties, the conductivity and the specific heat capacity, and the density of a material. And between them, that is what really goes to give us an indication of whether a material has thermal mass or it doesn't. So starting at the bottom, air has no thermal mass, okay? The specific heat capacity of air is not bad on the face of these numbers, but its density is tiny. So a cubic meter of air has the ability to absorb about 1 kilowatt of energy per second per degree of temperature rise. Okay? So let's put that in again. 1 cubic meter of air would heat up by 1 degree centigrade if you turned on an electric kettle element for about 3/4 of a second. It has no thermal mass, okay? There's nothing there to absorb that energy, in essence. Water has actually got pretty good thermal mass. It's got a very high specific heat capacity, and it's got a pretty good density. So if you can get an enclosed volume of water into a building, you can use it to store thermal energy. And that's one of the reasons why boilers and radiators and heating and cooling systems all run on water, because water is a pretty good way of storing and transferring energy. But it's not terribly useful as a building material, so we tend not to. Wood has actually got fairly similar characteristics to some of the other thermal mass construction elements, but we don't use it in enough quantity to make up for the shortfall in density. Yeah? Again, it's like air. There's not enough. There's plenty of wood in a construction like this. There's plenty of surface and there's plenty of wood, but actually there's not much density to that timber, and therefore it doesn't make much of a contribution to the thermal mass. It's got some, and it's measurable, but it's not as useful as what we might think. Now I put steel brackets galvanized in there because there is the myth around that you can put a wriggly tin deck former in and cast a composite concrete deck on top of it, and that'll have all the thermal mass of an exposed concrete soffit, and it won't. Okay? For two reasons. The problem with metals is, although they've got a high specific heat capacity, they've got a huge thermal conductivity, which means that if you introduce heat at one point in one room of a building, you might want to store it for later reuse. Actually, that heat just dissipates throughout the metal structure, throughout the connected metal structure, and it's gone. Okay? So there's no localization to the storage capacity, which is actually a key element of thermal mass design. We want the capacity to absorb and store energy in the rooms that we're dealing with, not over the whole building. The other thing about metal is the emissivity. Now, emissivity is a scientific term. It compares the ability of a surface to emit a full spectrum of radiation compared to a black body. Now, a black body is a theoretical object which emits electromagnetic radiation equally across the entire spectrum. You don't need to know that. As far as we're concerned, this is a number. I'm sorry, I got carried away there. This is a number between 0 and 1, which in effect represents the surface capability to absorb and re-emit energy by radiation, which is very important to us, because in a building like this, we're all sitting here as hot bodies, okay? We have a surface body temperature, clothed, of about, sorry, I'm covering my microphone, of about 30 degrees, 28 to 30 degrees, which is quite a lot warmer than the surface temperature of the walls and the floor and the ceiling surrounding us. So we actually lose quite a lot of our metabolic heat by radiation to the surfaces that surround us, not just by convection and conduction into the air. What that says is that our ability to radiate heat to a metal surface is actually very low, and most of that heat is reflected straight back to us. So even if we could make use of the specific heat capacity and the density of the metal, we can't in a building situation because you can't get the energy into it. It doesn't absorb the energy. It acts like an insulator, in fact, to a thermally massive structure. So we come back to our old favourite, the reason why we're all here, concrete. And concrete happens to have just about the optimum combination of density. So there's plenty of mass, physical mass, in an element of construction. It's got low, but not terribly low, thermal conductivity. It's got enough thermal conductivity that energy that's being absorbed in the surface will penetrate into the depth of the structure, but not so much that it dissipates everywhere. It's got a good specific heat capacity, good ability to store it, and it's got a very high emissivity, which means that it absorbs most of the radiant energy that falls on its surface. And that's why we like masonry construction. It doesn't have to be concrete. Stone, brick, and other forms of dry, dense, compacted materials, such as limecrete, things like that. These all have the property of thermal mass. Thermal mass is not equal. Thermal mass is more effective when it's in the upper portions of a typical room than when it's at floor level. And I often hear architectural students talking about thermal mass. It's okay, I've got loads of thermal mass in my building because I've got concrete floors. What have you got on the ceiling? Dry lining. The reason that it is so much more efficient at the top is because in an office situation or a typical building situation, the radiation that goes on from our body surfaces takes place with the tops of the walls and the ceiling because the floor is sheltered by furniture. It's as simple as that. And also heat rises, so it tends to be maybe a degree or degree and a half warmer close to the ceiling than it is to the floor. So you're getting more conduction into the thermal mass. So even though you've got thermal mass in your building, how you deploy it within the space is also important. So on to Innovate. That's what it looked like about 18 months ago. The building was designed to demonstrate, as I said, a whole host of environmental design topics, including efficiency of resource use. And in order to make an efficient structure and in order to maximize the opportunity for thermal mass coupling with the environment, we worked very hard on persuading the developer and the funders to let us have exposed concrete finishes internally. Not just the soffits, but the wall panels as well. The only way we could get a decent quality finish was to make sure that we have a struck finish on the inside face, which is capable of being painted directly, which meant going precasting, because the only place we could get that quality of finish would be in a precast works. The panels were designed with the window openings, obviously. designed to fit the 1.5 metre module of construction. So obviously each of those centre to centre on the windows is 4 metres. 4 window panels or 4 window elements makes up one bay of the construction. Do I need to go into precasting? It's fairly straightforward stuff. I'm sure you're all fairly familiar with it. The Thermodeck you may not be so familiar with. Thermodeck is a system patented by some Swedish guy a few years ago, exported throughout Europe as a concept and now exploited totally in the UK, totally exploited in the UK by Tarmac. It's a system which takes any old hollow core precast floor slab, could be Bison, could be Tarmac's, could be anybody's, to be honest. And the clever people at Thermodeck come along with a core driller and they cut some holes into the soffit of the slab, connecting into the cores, and they cut a core either through that way, perpendicular to the cast cores, or they cut a series of sort of plugs out in order to make connections between the cores internally to the plank. They then plug up various bits of it in order to create this serpentine labyrinth within the plank using one or more or multiple cores in order to pass the air through the inside. The reason for that is when we construct a building which uses thermal mass in the walls and the ceiling, we're really only engaging with the first 20 or 30 millimetres of the construction depth, and that's down to the relatively poor thermal conductivity of the concrete. If we push heat energy into a concrete surface for 12 hours and then turn the heater off and let it cool down again, we can measure the penetration of the heat on a typical diurnal 24-hour cycle, which represents a building. And it really is only expressed in the first 25 to 30 millimetres of the depth. So if you've got 175 or a 250 deep slab construction, you're wasting all the potential thermal mass in everything above the 25 millimetre soffit level. However, of course, the cover of the slabs is typically going to be of the order of 50 millimetres. So by passing air from the building down the centre of these cores, we're not only engaging with 25 millimetres at the soffit, we're engaging with 25 millimetres circumferentially around each of the cores. And if you look at the profile of a typical Bison plank, that's just about every ounce of the mass of the concrete that you're using for heat storage. It increases the thermal capacity of the building mass by a factor of 4 or 6 or something stunning. Anyway, so that was all about thermal mass and why it's really, really good in terms of reducing heating loads and things like that. In the event of the Innovate building, the effect of the super insulation and the thermally massive design with heat recovery meant that the space heating carbon footprints reduced to about 12% of the building total. The air conditioning, cooling load stayed about similar. It's reduced in proportion to the overall, but it stays about the same as a proportion. And that meant that re-examining this building now in the light of thermally efficient construction, you can see that lighting is the next biggest issue that we deal with. And so the building's designed for daylighting. This is the section that I thought I had in earlier. Describes the 2 wings of the building, 1 2-storey wing, 1 3-storey wing, and a central glazed atrium, allowing sufficient daylight penetration. The reason for 2 stories on one side and this slopey bit of glazing to the atrium roof is to get sufficient sky angle available at the ground floor down here. We're getting about 40 degrees of sky angle at the window surfaces down here, whereas if the atrium had been enclosed on both sides by 3-storey construction, the sky angle at that window would have been reduced to about 17 or 20 degrees. So that would, producing a 50% fall off in the amount of daylight that's arriving at that window. So this building form was governed by lighting issues just as much as it was governed by thermal issues. Unfortunately, of course, this office window down here suffers from the overhanging of that, but in overall terms, that's only 10% of the entire office accommodation in the building, which suffers from less than the design daylight level. The building was orientated very specifically on the north-south axis. And there's a lot of debate about which way buildings should face. Should you face them north-south in order to exclude the midday sunshine at the south elevation? Should you face your main elevation to the south because it's easier to do the calculations on the solar shading? My argument is that if you're only facing your building south to make the calculations on the solar shading simpler, you're being lazy. And actually, by putting a big overhang above a window on a south-facing elevation, you're blocking out maybe 70% of the available daylight. We've seen, once you've dealt with the thermal issues, the lighting is the biggest issue. I think you should face your buildings east and west, so they don't face into the direct midday sunshine, and you can get as much daylight in as possible. But also looking at just some of the other features of the building and the way it sits on the site. This is what I was saying about the daylighting. Yeah? On a window without an overhang above, you've got nearly the entire hemisphere of the sky vault available to project light onto the centre of the window. A big overhang above the window in this point here, you can see, would cut down the available skylight quite dramatically. And it's the light from the top of the sky, where it's its brightest, is its most useful. 70% of the daylight from the sky comes from the top 30 degrees of the sky vault. So the effect of lighting a building with daylight is to reduce the amount of energy you need to burn for artificial lighting. People ask me, why didn't you put PVs on your building? And I say to them, well, kind of perverse really, isn't it? I've got a window which lets in 100% of the solar energy available as light, and we use it. I could block that window up and just do a normal facade, and we could put photovoltaics on the roof to run the lighting instead. So you'd convert 12% of the available solar energy into electricity with the PVs, and you convert 85% of that back to light in an electric light fitting. What's wrong with windows? Well, I think we've forgotten how to use windows. This is a plot of daylight availability from the unobstructed sky. For our design daylight factor of 4.5% in the offices, anything within the green part of the diagram is lights off. Anything within the yellow part of the diagram is light fittings modulating, dimming in order to keep the light levels up to appropriate. And anything within the red parts of the diagram are periods of time when the lighting is required on full. These are all the days of the year along the bottom. These are all the hours of the day at the side, and that's typical office occupancy from 8:30 a.m. to 6 p.m. And what that shows us is that by daylighting offices, you reduce the number of hours that you need artificial lighting by up to 80%. I mentioned mentioned the prefabrication process. The off-site construction was principally about the quality control on the surface finishes of the concrete in order that it could be brought, struck finish, brought from the works, erected on site, painted, job done. Very important, in fact, because the prefabrication of these elements cut down the construction time on site hugely. If you imagine the comparison between a framed and clad building and a wall construction, panelized wall construction, in one site operation, we put up the building frame, we put up the secondary structure and the principal element of the envelope, providing water tightness and providing air tightness, providing the thermal mass, in one element. And if you were doing that in a framed building, you'd be putting up the primary frame, you'd be putting up the secondary steelwork or whatever, the cladding rails, you'd be putting up the cladding system, you'd be lining the cladding system, you'd be dry lining it, it just goes on forever. Light aggregates were specified in the original mix specifications. CV Buckens did a number of trial panels, and in the end they elected to use quarry sand in order to get a decent surface finish. So unfortunately we didn't get to use light ag fines in the mix, but we did specify and did use light ag coarse aggregates. And we hoped for a better proportion of pulverised fly ash in the mix, but we were there faced with the commercial reality of a large precasting works. They've got a very, very big turnover of work. They've got orders stacked up, waiting to go through the works, and what they didn't want was to be waiting for any extended periods of time before they could strike the panels from the shutters. So they were geared up to really quite a fast turnaround, and that limited the amount of PFA that we could include in the mix. But nevertheless, it's there, and it's there in as much proportion as we can accommodate. And by specifying UK-sourced steel for the rebar, rather than Czechoslovakian or Polish or Chinese, it means that you know that that's coming from sources of recycled material rather than virgin material. The handrails were prefixed so that there was a safe working platform in place as soon as the wall panels were up and the slabs were in, and they were just dropped into place by crane, stitched together using dowelled and grouted joints between pockets left in the panels and pockets cut in the ends of the slabs. This was quite an interesting coordination issue for the structural engineers, because actually coordinating all of those joint pockets with the various drillings and cuttings that were going to be done for the thermodeck as well made life quite complicated, but they got through it in the end. And that's an example in situ of one of the dowelled grouted joints. This is obviously the outside face of the struck finishes on the inside face ready for decoration, and then the outside face was covered with insulation and external render. Just an example of the kind of issues that the guys had to deal with in terms of coordinating mechanical and electrical installation. In this case, the duct connections to the thermodeck. The building has a central line of beams, as you would expect. Unfortunately, the ductwork can only run down one side or other side of the beams, but it's got to connect to the thermodeck slabs, which are both spanning onto the beam. So you've got to get through the beam somehow, because if you go over it, people walk into the ductwork. And it was just to indicate the amount of detailing that had to be done for reinforcement. This was one of the issues, actually. We wanted to achieve, for a certain number of the panels, we wanted to achieve a struck finish on both faces, so that where the panels opened onto the atrium, we could just paint them and leave them as exposed thermal mass in the atrium. Unfortunately, when it came down to the reinforcement detailing, the very slender column elements in the panels meant that there was a lot of reinforcement in there, and Buckens were considerably worried about being able to get the aggregate down through if it was poured in a vertical shutter. So we had to accept that those were then poured on a flat bed, typically, and we ended up having to dry line the inside of the atrium to cover up the snotty face. Resource conservation. The ideas of resource conservation permeated throughout the construction contracts. The architects produced a 4-page spreadsheet questionnaire which went out to every supplier and every sub-supplier and every subcontractor on this job, identifying the materials and, principally the materials and the components that they were going to be installing, where they came from, how they were sourced, whether they were managed under any kind of the environmental certification schemes, for instance, Forestry Stewardship Council certified timber, identifying where the original raw materials were sourced from. So we've got a measure of the material miles embodied in this building, not just the carbon and all the other things. So sustainability was very much a part of the contractor selection and procurement process. And when it came down to site, you entered the site gate, and right in front of you was the recycling centre, very deliberately located there by the main contractor, so that everybody's awareness of material conservation was right there as you walked into the site. Separating out you know, it seems like kind of Mickey Mouse stuff, but it doesn't happen on sites. You look along here, you've got metals, you've got skips full of metals. Those don't go to landfill, they can be sold. Yeah? And the contractor actually made a tidy little back pocket profit sum out of recycling and selling materials off this site, rather than just dumping them all into one set of skips and landfilling them. And of course you're making money out of that rather than paying landfill tax. And ultimately this all-pervasive ethos of conservation on the site and the use of off-site construction techniques meant that the contractor estimated that they sent about 20% of the rubbish off-site that they would normally do from a traditional construction site. This is having a look at the exterior face of the building. As I said, you know, on-site fantastically quick. You put up the panels, you stick the windows in, you put some of this expanding gunge around the window frames, and you've got an airtight, watertight building which is ready for the finishing trades to start working inside. All in one operation, all in 2 operations, rather than the 5 or 6 associated with conventional frame construction. I've got this one here because these are the brackets for solar shades. You can see the projection from the face of the window at that point. You can see the depth of the bracket overall at this point. The rest of it's insulation. That's 3 boards of compressed foam insulation behind the brick plinth. But the real story is up here on the rest of the walls. The difference in the thickness there is also insulation. I'm proud to say this is the only job I've managed to do so far where I've contributed more to the wall thickness than the structural engineer did. The load-bearing concrete panels are 175 millimetres, the insulation is 250. And that's the kind of thicknesses, that's the kind of ratios that you need to be working with in order to get down to these super insulated levels. That's just another photograph of the showing you. That's the complete block. It was polystyrene block insulation glued, bonded and glued to the face of the concrete, and then finished with a stow render system. The Thermodeck system, as I said, you put in any old concrete plank, Thermodeck comes along and they drill out these cores, or they drill these holes connecting into the cores in the planks so we can activate them. And then you plumb this up to the central distribution air ducts with all these pretty little bits. Don't have to be spiral wound, you could use anything, but in this instance the architects, for reasons of demonstrating what the building was about, chose to make the connections to the Thermodeck explicit. The way the Thermodeck really works, I've told you about thermal mass and how that works. The way the Thermodeck really works in a system, heat is generated, hot air is generated by people in offices. It's extracted out of the building using a big fan on the roof. We put that hot air through a heat recovery wheel, which cycles with the fresh air that you're pulling into the building to deliver to the office. So you're recovering excess heat from the exhaust air in winter onto the outside air. That warms it up to a point where it should be comfortable. If there's any excess heat, the fresh air coming into the building becomes overheated. Okay? But we then circulating it through the Thermodeck. So if the fresh air is overheated, it gives up its energy into the Thermodeck. The Thermodeck stores it, and by the time the air comes out into the offices, it's at a comfortable temperature again. But we've got that excess energy locked away for later reuse. Now, later on, if somebody turns all the computers off and goes out to lunch, the amount of heat recovery drops, so the supply air temperature, the fresh air temperature drops. It would become uncomfortably cold, but we're now pushing cold air through a warm Thermodeck slab, so it draws the heat out of the concrete, the fresh air is warmed up, and it still comes into the office at a comfortable. That's how we get the energy storage. It works very similar in summer, only we use cold outside air at night to discharge heat from the building, and we continue running that system until we've stored enough cooling energy in the Thermodeck slabs to offset the next day's heat loads. And if we can't do it just by cold nighttime air, then we run our little chiller, as I indicated previously, 24 hours a day, to store energy in the slabs when the building's empty and to contribute to the cooling load in the summer when the building's occupied. It all goes on in these bits of kit on the roof. It's just a photograph of an air handling unit, sorry, I couldn't resist. That's the photograph of the CHP unit, because everybody has to show a photograph of a CHP unit in lectures like this. But one of the more interesting features for me was that this is the first time in an office building that anybody has used vacuum drainage. Vacuum drainage is nothing new. If anybody's ever been to the loo on an aeroplane, they know exactly how it works. You press a button, a valve opens, there's a big difference in pressure between inside the aircraft and outside the aircraft, and it all just gets shot out, okay? You can't do that in a building because you're not at 20,000 feet. So you generate the difference in pressure with a big vacuum cleaner, and you connect that to pipework to the same sort of pans, well, slightly nicer than you get on aircraft. And when you press the flush button, again, same thing happens. It all gets sucked out by this big vacuum cleaner. And the reason for that is, in the 19th century, very clever sort of urban sanitation engineers, people like Bazalgette, decided that the cities needed cleaning up. And the best way to get sewage and waste out of the cities was to float them out on water. Because most of the waste that we produce floats, more or less. And if you push it along with enough water, eventually you'll get it out of the city to where you can deal with it in the countryside where the peasants aren't going to complain too much. And what this means is that we produce enormous volumes of sewage for a very small amount of actual waste. And all of that volume has to be dealt with at sewage treatment plants because it's all contaminated. In a vacuum drainage system, water is only used as a lubricant in the pipes. It's not used as the means of actually carrying the waste. So in a vacuum system, in a conventional system, you'd push the flush handle and between 6 and 8 litres of water would disappear down the drain in order to convey the sewage. In a vacuum system, it uses 1.2 litres of water, just as sufficient lubricant in the pipes and to give the pan a wash down at the end. So it represents an 80% reduction in water consumption. When this vessel fills up with enough liquid, okay, it's then pumped out into the gravity sewer, where because there's liquid content, it floats away as it would do normally. But it's highly concentrated. It's not it's not diluted with all this extra water. It's now highly concentrated sewage, which means that the sewage treatment works can be smaller. It has to cope with less peak flows. It has to cope with less overall flows. And it can work much more efficiently because the concentration of sewage is much higher. In our terms, it means that reducing the water consumption for toilet flushing by 80%, we can derive all of the water we need for toilet flushing off the roof of the building. Typically, you'd put in tens or 20s of cubic meters of water storage in an office building for rainwater, and over the course of a year, you'd perhaps get 60–70% of your flushing requirements from rainwater, based on your old style 8 litres a flush. 1 litre a flush, 1.2 litres a flush. The requirement for water is so much reduced that you can't realistically do it entirely from rainwater. So the consequence of that is, overall, the building are reduced by about 75% volume, and the water consumption, the mains water consumption, is reduced by about 80%. Put all of the conservation measures, put all of the energy issues together, and compare it to the national benchmarks. The Energy Efficiency Best Practice Programme has been surveying UK buildings for the last 30 or 40 years now, and coming up with benchmarks for typical air-conditioned office, typical headquarters office, naturally ventilated offices of various kinds, and looking at where the UK building stock sits. And typical is your average UK building. Good practice was the best of what was being done 10 years ago, right at the top edge, probably equivalent to a good BREEAM plus Building Regs 2006 these days. And we put the Innovate Green Office in, just in case you missed it, it's right there. It's an air-conditioned building. It's got comfort cooling. It's got climate control in the summer to limit the temperatures. So it sits alongside the normally air-conditioned developer offices. And yet, in terms of its carbon performance, it's actually right down with sort of the best practice in terms of naturally ventilated buildings. And that's down to the thermal energy storage, and it's down to the operation of the plant with heat recovery, and it's down to the operation of the CHP. So it is possible to deliver mechanically ventilated, air-conditioned buildings which perform every bit as good as naturally ventilated. In overall terms, if a conventional air-conditioned office, and this would be any of the previous offices by the same developer, Innovate, if a typical air-conditioned office is produced carbon emissions equivalent to about 75, 76 domestic units in a year, this building, Innovate Green Office, will produce a carbon footprint equivalent to about 16 domestic units. A domestic unit being your average 2 up, 2 down, 2.2 children, whatever it is. The real saving is just about 350 tonnes of carbon dioxide per year. So, summarise the results. Designing with thermal mass and designing with a reasonably intelligent strategy for lighting and for control of the much smaller plant than you would otherwise have resulted in 80% lower carbon dioxide emissions than a conventional office building. As I've just highlighted, 80% lower mains water consumption than a conventional office building, 75% lower sewage discharges than a conventional office building, and based on the evidence that the contractor gathered, probably about 80% less waste sent to landfill during the construction process. Not insignificant numbers. The job was awarded 87.55% under the BREEAM for Offices 2005 assessment, which is the highest score ever achieved by any building measured under BREEAM. One of the key results for the developer was the financial return, which justifies taking this prototype building and turning it into a repeat building. I mentioned right back at the beginning that the cost of this one was about £135 a square foot compared to the developer's previous offerings at about £85 a square foot. That extra over cost has to be funded from somewhere. Now, quite a large proportion of that was non-repeatable costs associated with the extra design fees, the extra time involved, the prototyping, the testing, and the various adjustments to the procurement methodologies that were required by this as a first-of-kind building. Next time, those costs won't recur, but this is still a more expensive building than the developer's previous model, and that's got to be paid for somehow. So it's paid for by amortizing the running cost reductions. Now, when we started the project in 2002, if we looked at the benchmark for a typical air-conditioned office in the UK and did some calculations on it using energy prices at that time, we could predict that a typical office would cost £1.42 per square foot per year in energy. In fact, the Innovate office at Sherwood Park in the same year cost £1.40 a square foot to run, and so is almost bang on that typical developer building benchmark. Now, when we made some predictions of the likely running cost of the green building, it was sufficient to persuade the developer that there was a product there for future speculation. And then, as happens, luck was on our side, and during the design process, between the inception of the design of this building and the delivery and handover of this building, energy costs went through the roof. You know, typically clients experienced energy cost rises of between 40 and 100%, depending on your buying power in the commercial sector. And that meant that when the building was delivered, the running cost of the previous offerings had gone up to about £2.24 a square foot, whilst the running cost of the Innovate building, the green building, sorry, was 65 a square foot. They're not there yet, it's not achieved it yet because it's not fully occupied and it's not fully working. But the saving there represents about £1.50 a square foot a year. Doesn't sound like very much until you look at the financing that a developer looks at when they're trying to rent office space. On this particular office park, on this particular bit of Leeds, office rentals for a bog standard office would probably be around about 17 or 18 pounds a square foot a year. For Innovate as a premium building, maybe up to 22, 25 pounds a square foot a year. Now, as a proportion of 18 pounds a square foot a year rent, £1.50 a square foot less operating cost to realise that rent actually represents 8% profit that you don't have to do anything to earn. Typical developer's margin may be of the order of 8 to 10%. So potentially you're looking at nearly doubling the profit that the operator is making on this building by reduced running costs. We always talk about running cost reductions in terms of the capital cost of buildings, which is entirely the wrong way to look at it, because that's not the way that people appraise buildings in terms of their value. People appraise buildings in terms of their rental return. And if you examine running cost savings in those terms, they can make a very significant difference to a bottom line. If you went to a developer and you said, I'm going to increase the cost of your building by 25%, and it's going to take you 25, 30 years to recover the capital element against the running cost savings, they'd kick you straight out the door. If you go to the same developer and say, on your rental, on your expected rental return of 18 to 20 pounds a square foot a year, I'm going to give you an increase of profit of between 50 and 100%, they'll bite your hand off. And at the end of the day, there is no point in being worthy but dumb. Okay? There is absolutely no point on earth in designing highly performing, highly efficient, very, very worthy buildings that nobody wants to work in, nobody wants to live near, nobody wants to visit. So you've got to produce a beautiful icon. And I think Rio Architects have done a stunning job on this building, as hopefully the following photos will evidence. We want this building to be an icon so that people look at it, people appreciate it, and potential customers for office space go to other developers in the market and say, why can't we have office space like this? Because it's by making that market pressure on the commercial developers as a result of producing offices with character, buildings with character, and ones which push all the buttons in terms of their corporate social responsibility, that we can start to move the market towards developing more green buildings. And it's not just about the finances, although it is very much about the finances sometimes. And I'll leave you with the credits. Innovate Property as the developer. Rio Architects, if anybody wants to check them out, they're a little practice in Cardiff. Cameron Taylor were the structural engineers. I know there's somebody from Scott Wilson here tonight. I saw the badge upstairs. Us as the environmental engineers. Project managed by an outfit called Myrus from Solihull. GMI Construction, main contractor based in Leeds. Buckens as the precast frame contractor. They're also up in this part of the world somewhere, aren't they? Not very far away. And I mentioned the M&E subcontractor, Good Marriott and Hurst House, simply because they're local as well and played a very, very important role in integrating it all together. Thank you.